Hello, good evening, and welcome to the next exciting episode. We're going to move on from reflection today, and we'll cover the topic of refraction. Uh, Reflection, as you already know, is when light hits a surface, a reflective surface, and bounces off. Refraction is where light hits a surface of an object, and instead of reflecting off, it passes through. So the type of objects we're talking about today, we'll call those transparent. Transparent objects are things that allow light to pass through them basically in straight lines. So before we move on, please don't confuse refraction with reflection. Make sure you know the difference. And actually a more common mistake is confusing refraction with diffraction. Don't make that mistake either. Diffraction is, as we've already seen, the spreading out of waves as they pass through a gap or they pass over objects. Okay, so now I've got that out of the way. Before I continue, the diagram above my head is kind of the classical diagram of refraction. It's a ray of light passing through a glass block. I won't go through the details yet. I'll put a bigger version of that on the screen so you can see it better. But if there's one takeaway from this little talk, it's that you kind of memorize what that diagram looks like. That's everything you really need to know about refraction. The only other thing is we need to cover one new formula. I'm sure you're happy to know that, but it's basically only one formula. Okay, so before we continue, have a look at these diagrams. First of all, you're probably all familiar with this. If you've got you put a pencil into a glass of water or a straw into a glass of water, it looks as if that object is bending. Now you obviously realise that when you put a pencil into a glass of water, the pencil doesn't automatically bend, so therefore it must be an effect that the water is having on the light that's passing from the pencil to your eye. Similarly, I don't know if any of you are experienced spear fishermen, I very much doubt it, but if you're spear fishing, apparently, I don't know this for certain, but apparently if you're spear fishing, you learn that you don't fire the spear towards where you think the fish is. You actually aim above the fish. Now the reason for that is we've got two fish here. This is the position of the real fish, and here we've got what the fisherman perceives as the position of that fish. They're in two separate places. What the fisherman is actually perceiving, the red line, is actually the virtual image of the fish. Now the reason for that is the fish is here, light heads away from the fish, hits the surface of the water, and as it hits the surface of the water it bends in just the same way as light from the pencil bends, and then heads towards the fisherman's eye. The fisherman's brain, up here, then produces an image of the fish, and because your brain knows that light, or the brain only perceives light as moving in straight lines, the brain calculates, using a straight line, where it thinks the fish is, and he sees the fish actually in this position. Okay, I hope that made sense. So that's the basis of refraction. Here's a bigger version of the diagram above my head that will explain everything hopefully a little bit clearer. Okay, so here we have a glass block. We're going to shine a thin ray of light, possibly a laser beam, towards the surface of the glass block at an angle. You're familiar with this. We draw in a normal line that's at 90 degrees to the surface of the block, just like the normal lines we saw with mirrors. It's at 90 degrees. And this angle here we'll call I1. That's the angle of incidence of the ray of light moving from air into glass. As the ray of light hits the glass, it bends, or we should say it refracts. And it refracts towards the normal line. This angle here we're going to call R1. It's the angle of refraction 1. Just to confuse you, we used I and R similarly for mirrors. In this case, angle R is not the angle of reflection. We're going to call it the angle of refraction. We use small r for both of those. Okay. It actually bends or it refracts. The reason being is that it slows down. Now, you're used to talking about one universal speed of light, but the speed of light is not universal. The speed of light actually changes depending on the medium that the light is moving through. And because glass is more dense than air, the light actually slows down. As it goes to more dense materials, the light slows down, and because it slows down, it bends towards the normal. Okay, and then at this surface, it's the second surface. At this point, the light is moving from the glass into the air this time, the other way around. And this time, as it hits the surface, it refracts again, but in this case, it refracts away from the normal. And here we've got a second angle of incidence, and here we've got a second angle of refraction. Please note that it's very important whenever we come to measure, hopefully when we get into the lab, whenever we measure these angles, we always measure away from the normal line. So the first thing you always do is draw in a normal line at 90 degrees to the surface that you're measuring from. Okay, I hope that made sense. That's basically refraction. It's light being caused to bend because it's moving from one material or one medium to another medium and either speeding up or slowing down. In this case, as it goes into the glass, it slows down, bends towards the normal. And in this case, as it heads out of the glass and into the air, it goes to a less dense material and therefore bends away from the normal because it's speeding up in this case. So just before I move on, possibly worth me saying this, a very common mistake is that when you're drawing these diagrams, it's to forget whether you should be drawing the ray of light moving towards the normal or away from the normal. It sounds pathetic, but when I did my GCSEs, I came up with this. Less to more is towards. Okay? And what I mean by that is less dense to more dense means that the ray of light moves towards the normal line. Okay? So I'd like you to remember that. Less to more towards. And then obviously more dense to less dense is the reverse. It's away from the normal. Okay. Right, I hope that made sense. I don't want to spend too long on that because you can pause and rewind and go back through it and get back to me with any questions. I'm going to leave this video with as promised, a new equation. Now there's two equations there, but the only one that's actually on the syllabus is this one. And this equation has a great name. It's called Snell's law, and it's named after this guy you can see here, who has, I think, the best name in physics history. His name was Willebrord Snellius. He was a Dutch mathematician and physicist and astronomer in the 1600s. And if ever I was going to change my name, I would definitely change it to Willebrord Snellius. Okay, before I tell you exactly what this means, let me just introduce the idea of this thing. It's called a refractive index. An index in physics or in maths, we use the word index to represent any kind of number that's on a scale but doesn't have a unit. And the reason is it's basically usually always a ratio. So an index is a ratio. And the refractive index of any substance is the ratio of its speed in air divided by the speed of the light in the substance that you're interested in. Now that's actually not on the syllabus anymore, it used to be, so you don't need to know it, but that's basically what the refractive index is, and we call refractive index n. It has no unit, but it's got a symbol of n. N just stands for number. And the refractive index also equals the sine of the angle of incidence divided by the sine of the angle of refraction. Obviously, at this surface, this is I and this is R. And at this second surface, this angle is I and this angle is R. Okay, so as usual, in a physics exam, you'll be given 2 of the 3 things, and you'll be asked to calculate the third. If you're just being asked to calculate refractive index, they'll give you I and R, and you just plug in the sine of I and the sine of R into your calculator, divide one by the other, and you get the refractive index. There's a slight complication. If they give you refractive index and one of the other 2 angles, obviously the first thing is you rearrange the equation. So for example, if you're left with sine I equal refractive index that you're given multiplied by sine R, which you'll have been given, you're left with sine I. That's not the answer because they'll be asking you what is the angle I. In order to get angle I, you need to press inverse sine on your calculator to get the answer in degrees. Okay, alright, so that's refraction. I hope I didn't go through it too quickly. I think it's fairly straightforward. As usual, please just get back to me if you think I've not covered it very well or if you've still got questions. And I'll think about setting this for you with some past paper questions that you can try. Okay, take care everybody and look after yourselves and look after your own health and that of your family. And I will speak to you at some point over the next few days. Okay, goodbye.